Hello, everyone. My name is Yingchen.
And my name is Ricardo. And today we will tell you about a new class of side-channel attacks called Hertzbleed. Power side-channel attacks and remote timing attacks used to be two disjoint classes of attacks. On the one hand, we have power side-channel attacks. These attacks allow to infer very small changes in a program's execution, but they require access to power measurement interfaces. And on the other hand, we have remote timing attacks. These attacks could only detect coarse-grained changes in a program's execution, but they can be performed without access to any special measurement interface. In this talk, we introduce Hertzbleed. Hertzbleed bridges the gap between these two disjoint classes of attacks by allowing to turn power side-channel attacks into remote timing attacks. This way, Hertzbleed makes those changes that up until today were only detectable with power side-channel attacks detectable even with remote timing. And as we will see, this has real implications to security because it can be, for example, used to leak cryptographic keys via remote timing, even from cryptographic implementations that follow constant time programming. The mechanism that enables this new class of attacks is dynamic frequency scaling, also called DVFS. In this presentation, we will first tell you about how and why DVFS leaks on modern processors. We will then explore how to mount remote timing attacks on cryptographic implementations. And then finally, we will discuss the broader implications of Hertzbleed to security. Let's start from looking at DVFS on a modern Intel processor. When we run a workload on a modern Intel processor, this is what the processor frequency looks like during the workload's execution. On the left-hand side, you can see that the processor runs at a frequency of 4.5 gigahertz for a short amount of time. This is what we call the max turbo state, and it allows the processor to have a boost in performance until the processor hits a certain thermal limit. After that point, the processor runs at what we call the steady-state frequency. The steady-state frequency in this case runs between 3.9 and 4 gigahertz and can last until the workload execution finishes. Our analysis focuses on the latter, which is the steady-state frequency. And in particular, the key observation of our work is that steady-state frequency depends on power consumption. For example, consider two workloads, workload 1 and workload 2, that normally have different power consumptions, as shown in this diagram. What we observed is that when we run these two workloads on our processor, at steady state, they run at two different frequencies that reflect their power consumptions. For example, in this case, workload 1, that consumes more power, runs at a lower frequency. And this is an important observation because, as we will see, it allows to turn power side-channel attacks into timing attacks. Now, power side-channel attacks have been known for a long time. And over the past 25 years, one thing that we have learned is that power side channels allow to infer very small changes in a program's execution, as I said earlier, such as changes in the data being computed on. So it's natural to ask the question, does this frequency side channel also leak information about the data being computed on? And to answer this question, we constructed a constant time workload with a fixed set of instructions. And in this workload, we only change the data values being computed on, namely the input. Now, in our workload, and just as we know from prior work, changing the input will cause differences in power consumption, as we can see in the diagram to the left. What we observe is that changing these inputs also reflects in changes to steady-state frequency on our processor. Now, from now on, we will only talk about steady-state frequency that we will just refer to as frequency. But for the sake of this presentation, the message that really is important, as we will see, is that changes in the data being computed on by a program can reflect to differences in CPU frequency. As we will see, this is the key observation that will allow us to mount remote timing attacks, even on cryptographic implementations that were considered secure against timing attacks up until today. Now, let me give you an example. Consider this function sum that computes the sum of two arguments, first and second. And let's suppose that we run this function as part of a program, for example, a cryptographic program, with two different sets of test inputs. test 1 and test 2. We can ask the question, which of the two tests functions runs at a higher frequency? So we can think about this question, and it turns out that perhaps counterintuitively, test 2 runs at higher frequency. The way we were able to answer this question in our paper was, and we were able to answer this question systematically for data, is by constructing a leakage model. And in our paper, we construct a leakage model for the dependency between data being computed on and power consumption or frequency on modern Intel processors. We find that there are 3 important effects that are independent and that affect this dependency: the Hamming distance effect, the Hamming weight effect, and the bit positions. I will now explain each of these effects, and then we will look at a case study for one of these effects before we turn into the security implications. Let's start from the Hamming distance. Suppose that during a workload execution, we have a computation that updates the content of a register AX, perhaps due to a shift, as shown in the slide. Now, when we have this computation, the Hamming distance is the number of bits that flip either from 0 to 1 or from 1 to 0 during this computation. In this case, the number of bit flips is 10, meaning that the Hamming distance is 10. On the other hand, in the example at the bottom of this slide, we have only 6 bits that flip between 0 to 1 or 1 to 0, meaning that the Hamming distance is 6. What we observed on our processors is that this feature of the data that is being computed on, namely the Hamming distance, does affect frequency. And in particular, the lower the Hamming distance, the lower the power consumption, and therefore the higher the frequency. And this is an important observation, as we will see for security. The second independent effect that we observed beyond the Hamming distance is the Hamming weight effect. Consider during a workload execution that we have a computation that looks like this, where it computes on, again, this register AX, but the number of bit transitions is 0, because there are no bits that flip during this computation. What we found is that the number of bits that are set to 1 in this computation, which is called the Hamming weight, affects the power consumption and frequency as follows. So consider in this case, we have a Hamming weight of 12. And in the second example, where we have less ones, we have a Hamming weight of 8. What we saw is that the lower the Hamming weight, the lower the power consumption, and the higher the frequency. This is important, as we will see, because it means that it will have particularly dangerous effects for cryptographic software that runs either low or high Hamming weight or Hamming distance data flows, depending on secrets. Finally, the third independent effect that we observed is the one of the bit positions. Now, what does this mean? Let's assume that we have a computation that looks just the same as the one in the previous slide, where we're computing on data, in this case with the Hamming weight of 8, and the Hamming distance is 0. What we observed is that the positions of ones in these data values does affect frequency as well. For example, in this case, we have ones in the most significant bits of this register AX. On the other hand, in the second example, we have ones in the least significant bits of this register AX. Both cases have the same Hamming distance and the same Hamming weight. And what we saw is that the second case consumes less power and runs at a higher frequency. And this is particularly important to keep in mind in the future, because it shows that even if the Hamming weight and the Hamming distances are the same across 2 different computations, the frequencies a channel can leak information about the positions of ones within data values, which is a surprising observation for modern general purpose processors. Okay, now you might be wondering, how did we come to discover this bit positions effect? And also, which bit positions inside data values affect frequency the most? And to answer these questions, let's now look at a case study of this bit positions effect. When we were studying the Hamming weight effect, so before we even looked at bit positions, we constructed a sender that looked like this. This is a workload which has an infinite loop of instructions that look just the same as the ones on the previous slide. And in this workload, we control the input, which is the content of all these registers. And notice that by construction, in this workload, the Hamming distance is always 0, and the Hamming weight and the bit positions purely depend on the input that we chose. So this workload allows us to fine-tune and to detect the differences that result from different Hamming weights or bit positions. And in this particular example that I will describe to you, we're going to look at the effect of different number of ones in this input. So here is an experiment that we run. In this experiment, we were changing the number of ones, either starting from the least significant bit or from the most significant bit. And on the x-axis, you can see the Hamming weight of this input, meaning the number of ones. And on the y-axis, you can see the average frequency at steady state. Now, as we discussed earlier, first observation that we can make on this data is that the lower the Hamming weight, the lower the CPU power consumption, and the higher the frequency. And this is important. We also show plots with the power consumption in the paper. But an important observation is that whether we start from the right, which is the least significant bit, or from the left, the most significant bit, there is a different slope in this trend. And there is a split in the center. Namely, this Hamming weight effect looks to be non-linear. And to dig deeper into this observation, we decided to run an additional experiment using the same workload, but this time we're setting for each byte, either that byte to be all ones or all zeros. And then for each byte within a 64-bit register, we were computing the delta in both power consumption and frequency to see which bytes had the largest delta. And this is what the results look like. On the x-axis, you can see that there is the byte index, 0 indicating the least significant byte, and 7 indicating the most significant byte. And on the y-axis, you can see the delta in frequency when that byte has been set to all ones versus all zeros. As you can see, the cost of having ones in the different bytes is non-uniform. And in particular, we can see that the cost of having ones in the most significant bytes is higher in terms of power consumption cost and also like frequency changes than the cost of having ones in the least significant bytes. And again, this is important, as I said, because it shows that it's not just differences in Hamming weight and Hamming distances that can be leaked through frequency, but even more minute changes, such as the ones about the bit positions. In the paper, we also describe a lot more experiments on each of these three independent effects. And we also show that these effects are additive and independent on modern processors. But for the sake of this first part of the talk, the takeaway really is that computing on data with different power consumptions, with different Hamming weights or Hamming distances, or bit patterns depending on secrets, can result in different power consumptions or CPU frequencies depending on that secrets. And now in the second part of the talk, we will show you how to exploit these observations to mount remote timing attacks on cryptography that up until today was considered secure against timing attacks.
So, in the first part of the talk, we say that frequency leaks data being computed on. Now we're going to show how to use the Hertzbleed side channel to launch a remote timing attack. Why can we even do that? The reason is very simple, because frequency and timing are equivalent to each other. The higher the frequency, the shorter the running time. Consider a 4-cycle program here. The number of cycles of this program is fixed. It is always 4. But when running on more than Intel CPUs, due to the frequency scaling, the running time might differ. Now we're going to show how to use Hertzbleed to launch remote timing attacks on a post-quantum cryptography scheme called SIKE, Supersingular Isogeny Key Encapsulation Scheme. SIKE is a key encapsulation scheme. It uses public key encryption scheme to secure a shared key. First, it has a key generation algorithm that publish a public key as well as a private key. Then it has an encapsulation algorithm that takes in the public key and outputs a shared key as well as a ciphertext of the shared key. In the end, it has a decapsulation algorithm that takes in the secret key and the ciphertext and output a shared key. Observe that the ciphertext C can actually come from anyone, a malicious attacker or an honest user. So this C can be anything. SIKE is a widely studied post-quantum crypto scheme. It has production-ready implementation from Cloudflare Circle and Microsoft PQ Crypto. It is currently in round 4 of NIST post-quantum crypto competition, and it is deployed by Amazon as a hybrid encryption scheme. We found a completely new vulnerability in SIKE that can enable a malicious attacker to trigger a large number of computations on zero, depending on a single secret key bit. We're going to explain to you about this vulnerability from a very high level. Suppose you're trying to extract the first bit of this secret key, SK. If the first bit equal to 0, such as a malicious ciphertext C prime coming from the attacker can trigger the decapsulation algorithm to output a partial transcript of the algorithm state look like almost random. However, if the first bit equals to 1, the same ciphertext C prime is going to trigger a partial transcript looks like all 0. From a very high level, you can think of the decapsulation algorithm works as if a for loop of A equals to A times Ri, where the Ri's are from a random distribution if first bit equals to 0. Whereas if first bit equals to 1, somehow a 0 jumps in at the very beginning, and once it appears, it is never going to go away. In fact, it will trigger a domino effect in the decapsulation algorithm of zeros. Of course, such an analogy is not what is really happening inside the decapsulation algorithm, but it helps understanding the attack. Obviously, with compared to first bit equals to 0, first bit equals to 1 will create a data flow with low Hamming weight and low Hamming distance, so that CPU consumes less power, runs at a higher frequency, and the program will execute in shorter runtime due to the Hertzbleed side channel that we just mentioned. Now let's look deeper into this SIKE decapsulation algorithm. The very first function called by the decapsulation algorithm is the 3-point ladder function. It takes in M as a static secret key and a ciphertext that contains PQ and Q minus P. It has a loop iteration, inside which it calls a subroutine X double and add, where the data flow depends on the current bit MI as well as the ciphertext. Now let's take a deeper look into the X double and add because that's where the vulnerability is. This X double and add function is very interesting. It is actually quasi-complete, which means it contains a corner case. The functionality of this X double and add is that it takes in U, V, and W and outputs 2U and U plus V, and W equals to U minus V. However, the corner case is that if W is one of the two special points, T the point of order 2, or O the point of infinity, this function will output 2U and 0, 0. You might wonder, what does 0, 0 even mean? Exactly, 0, 0 is meaningless. It is not even a point because SIKE operates with projective coordinates. As we saw previously, X double and add stays inside the loop, and the output of which is going to feed back to X double and add as input again. When the 0, 0 got feedback to X double and add as an input, either as U or V or W, the X double and add will output 0, 0 again. Let's go back to the 3-point ladder function. Suppose we're at iteration I, and somehow we put a T into the X double and add function as the third input. And this function will give us a invalid point 0, 0 due to the corner case we just covered. During next iteration I plus 1, this 0, 0 will be passed into the X double add function either as the third input or as the second input. It doesn't matter. This function will output 0 again. Let's recap. All we have said so far is that if a point t or o can be passed into the x_add function as the third input, this function will give us 0 and 0, and this 0, 0 will be passed into other parts of the function, creates a domino effect on low Hamming weight and low Hamming distance data flow. Is it possible for an attacker to trigger a t or o as the third input into the x_add function? In fact, yes. This observation leads to an adaptive Chosen-Ciphertext attack. Suppose the attacker knows the secret key up to bit k-1. It is possible to construct a ciphertext C' such that if the next unknown bit mk does not equal to k-1, the attacker can trigger a t as the third input into the x_add function and creates a domino effect on zeros. However, in the other case, such a t will be put into the x_add function as the second input, so there's no domino effect on zero. Such a domino effect on zero of SIKE cannot be exploited by any other prior timing side channels, because even though there are large computations on zeros, the number of cycles the program executes is secret independent. However, as we covered in the first part of the talk, Hertzbleed can turn low Hamming weight and low Hamming distance data flow into shorter program running time. Therefore, if mi does not equal to m-1, there's a domino effect on zeros, and the data flow has low Hamming weight and low Hamming distance, the CPU consumes less power, the CPU runs at higher frequency, so the program executes in shorter running time. In the other case, the program executes in longer running time. We can use such a behavior as an oracle to extract the secret key bit by bit, and that's how we design our Chosen-Ciphertext attack. We targeted two state-of-art implementation of SIKE. The first one is from Cloudflare Circle, written in Go. The second one is from Microsoft PQ Crypto, written in C. The second one is also NIST post-quantum crypto competition submission. We monitor the CPU power consumption as well as frequency. We confirm that when running decapsulations with mi does not equal to mi-1, we can trigger the domino effects, and the CPU consumes less power and runs at higher frequency. In the end, we launch a remote timing attack. We have a malicious attacker who can construct the ciphertext C' according to our adaptive Chosen-Ciphertext algorithm. We have a server that takes in this ciphertext and decapsulates it using either Circle or PQ Crypto and sends back an acknowledgement to confirm the establishment of a shared key. The malicious attacker inside this case will only time how long it takes to finish n concurrent requests, but nothing else. We're able to recover Circle full secret key bit by bit in 36 hours. We're also able to recover PQ Crypto secret key bit by bit in 89 hours. One thing to note here is that the timing signal is strong for top secret key bits as well as last secret key bits. The reason is that the domino effects on zero actually propagates beyond the three-point ladder function into other parts of the algorithm. Such a faulty behavior on SIKE is actually acceptable by its own threat model. However, due to Hertzbleed, it can be mounted as a remote timing attack. SIKE is only an example of the power of Hertzbleed. Now let's talk about the security impact of Hertzbleed beyond SIKE. Timing attack has been here for 25 years. During these 25 years, people have developed 3 different constant time programming principles to defend against timing side channel attacks. Hertzbleed showed that current practices for how to write constant time code are no longer sufficient to guarantee constant time execution. The reason is that Hertzbleed can turn power leakage into timing leakage. Here's another way to think about it. There are three factors that influences the program execution time: instructions per program, cycles per instruction, as well as seconds per cycle. Note that the third factor is actually the inverse of frequency. All previous timing attacks exploit the first two factors, and all previous constant time programming principles address the first two factors. However, Hertzbleed targets the third one, and that's why the current constant time programming principles are insufficient. How can we make sure that frequency variations do not depend on secrets? Now let's look at some mitigation ideas. First, we can disable frequency boost. When we're running our experiments with turbo boost off, we observe the CPU running at base frequency all the time, and we see no leakage from Hertzbleed. However, notice that this is only a mitigation but not a defense, and it incurs system-wide performance cost. Second, we can mitigate leakage in the ciphers themselves. For example, we can avoid data flows with largely different Hamming weight or Hamming distance, depending on secrets. But consider how large the input space of any crypto system is. It might be hard to guarantee this. Or we can apply data masking to internal computations of any program with hopefully reasonable overhead, so that the dependency between secret and frequency can be decoupled. With that, we would like to conclude our talk. And if you want to know more, please check our website or ask us questions. Thank you.